this is the measure of how spread your eigenstate is on the lattice. Okay, so it's not a thermodynamic entropy. Okay, I could have used also some participation ratios. Okay, all these things go between 0 and 1. And the gang of 4 tells us that if we write the beta function for one of these things, for example, d, but for phi is the same, okay, as d log d by d log v, okay, then the slope here is d minus 2 divided by d, and close to here, close to 0, okay, this thing has to go down like 1 over d log d, okay, negative, of course. So there is a transition somewhere over here. Now I've exaggerated a little bit the position of the transition, because essentially what happens is that as you increase from d equal 2, you go to 3, 4, 5. This slope goes towards 1. And in fact, what happens is that with this definition, okay, in which I take the derivative with respect to the volume, I can put all the beta function on the same picture. Okay. So the beta function for 3 dimension will look something like this. For 4 dimension will look something like this. 5 dimensions and so forth, and then we'll keep growing and going up, okay? Now, what does this mean? Okay, what does this curve mean? If I have my numerical data and I take these derivatives, numerical derivatives, okay, do I really see this curve? To a good approximation. In fact, what you see is the following thing. So you see, you start from a point which is not on the curve. Okay, so you pick a disorder W and some initial system size L0, and then you increase. Okay, you take W L0 plus 1, plus 2, plus 3, plus 4, you do your exact diagonalization, you compute your observables, take derivatives, and put it on a curve. And then what happens is the following. Initially, you have this little hair, and then you get attached to this one parameter curve. Okay? For example, if you are in 3 dimension, let's look at this lower curve here. If you start with lower, let me put a line here, a reference line, I will then explain to you what it is. If you start with lower disorder, the points start with the same L0, they start more to the right, okay, and they attach to this line earlier. Okay? If you start with larger W at a given L0, at a certain point you're going to flow in the other direction. You attach on this curve and then you flow down here. Okay, so this little hair is the subleading corrections to scaling. Okay, they are associated to an operator Y. So to an operator, some operator which lives in my field theory, which has a scaling dimension Y which is negative. And it's called irrelevant. Instead, the disorder is a relevant operator. Okay, because flow tends to flow away. Okay, good. What happens if you are exactly at the critical disorder? Okay, well, at the critical disorder, which has a given value, which has its own trajectory, has its given value W given L0, okay? It's not, it's not granted that the critical disorder is exactly, it can change a little bit. But let's forget for a second. So let's say you are exactly the critical disorder, and then this curve will flow here, and you get stuck there. Okay? In infinite RG time is the logarithm, the ratio of the logarithm of the volumes. Very good. You see these things in the data. Okay? So when you try to collapse the data, for example, now let me plot as a function of system size, okay, d, okay? We know, for example, if we start from W less than WC, that this thing has to flow to 1, okay, eventually. And it does flow to 1, it does something like this. Okay. And any disorder which is less than WC, okay, so this is W less than WC, this is W larger than WC, will do the same. With a little bit of these airs here will be these things here. Okay? Very good. Fine. So this is a way of analyzing, this is an agnostic way of analyzing the numerical data, okay, in which I have not done any rescaling. I'm just looking at the curves. If the curves show me a one parameter scaling like this, then I know that close by here, I can do a rescaling and show all the data are as a function, not separately of W and L, but of the combination L and Xi of W, where Xi of W is W minus WC to the minus nu. Okay, and yesterday I told you what was the relation between the slope here and the exponent nu. Okay, good.
Top curve you already did this cascade and divide by xi.
Here I'm just looking at this part of the curve going here. Okay,
Sorry,
so
remind me a little bit, because you say it's agnostic, so you are not
you're not assuming any scaling, you're just
assuming the single number.
in fact, it's not, if you look at it, it's not one parameter scaling because there are these little hair. So in fact, what this tells you is that beta is actually beta as a beta just a function of d, and then it has a function a beta 1, which is a correction, this little hair, which is a function of d and l or w, any, two parameters out of the three, which should be. Okay? Good. So this is fine. So, but as far as these things. Okay, now, good. The other thing is that you see a D-critical here, and that this D-critical moves down to 0 as I increase the system size. Sorry, the dimension, system dimension.
The only thing maybe is that depending on the dimension, it might be super hard to see the critical, right? Because you agree, just to be sure that I'm getting it's true, right? Because if the dimension is large, to see the critical, so to see the one parameter curve, you will need a normal system size.
Yes. Yes. But this is because the computational power scales like L to the D.
Exactly.
Okay. So you need to have very large. Okay, before we go to this thing, there is one thing that I wanted to show you.
If I don't go to very large system size, I will think that I have a two parameter scaling while instead I'm just seeing
Yes, yes.
Cases where
But
the beta one is
but when you do numerics, you realize that there are
Okay.
that there are just, you know, that it's
Yeah.
going to some form. Okay.
the many body setup.
Yeah, in the many body setup, it is a problem because it's not doing that. Okay, so also in the regular random graph, a lot of the numerics actually has a problem because of that. By the way, yesterday I told you let's to solve the the one parameter for d equal 2, which was beta of d was minus 1 minus d square. Anybody did that? Let me show you actually how you can, from this simple form, you can find that the scaling of the localization length is exponentially, it's as this strange form here. Okay, let me show you how it is very easy, just based on this equation here, to get this. Okay, before we go to infinite dimension. Okay, so the idea is the following. You have d log d divided by d log v, okay, is minus 1 minus d square, okay? Then we separate the variables. dd over d 1 minus d square is equal to minus d log v, okay? And then I integrate. And this is log of d divided by 1 minus d. Okay, now important thing. What do I mean I integrate? Okay, it means the following thing. This is my curve, okay? This is minus 1 minus d square, okay? So I start sorry, this should be is below, but comes with zero derivative, okay? I start at a given system size L0 for a given disorder W, and this gives me a certain D0. Okay? And then I follow this curve, and this connects me to another system size L, the same W, and some D of L. Okay? I want to see, inverting this curve, what's D of W and L. Okay, in order to do this, I do this. So this needs to be integrated between D0 and D, and this needs to be integrated between V0 and V. Okay? So if you do this, the primitive of this function is log of D over D plus 1 divided by 1 minus D. Okay? And then I subtract this log of D0 divided by 1 minus D0 minus 1 minus D0, and this is log minus log of 2 times log L divided by L0. Okay? So now I have my small system size L0, let's say, I don't know, 4. Okay? And my disorder W, which is pretty small because I started very close to 1. What's going to be the dependence on D0 on W? It's going to be 1 minus what? It's everything analytic. It's a 4x4 object, okay? And I'm asking, how does this measure of ergodicity goes as a function of W? It's going to be W squared. Why W squared? Because it's the disorder is symmetric, okay, as average 0. So I have a 4x4 thing. I can do perturbation theory, I'm really talking about a small system size. Imagine doing it in your computer. Okay, then you do very small w, and you're going that everything is going to be a function of w square. Okay, so this is approximately some w squared divided by w0 square. Good. Then we said that d0 is very close. W0 is some number that depends on L0. Okay, some constant that depends on L0. The RG flow guarantees that it doesn't matter what L0 and W0 I get, they will flow together. Okay, so D0 is very close to 1, so this term is dominant with respect to this one, so let me drop it out. Let me rewrite this function as log D 1 minus D plus 1 minus D is equal to minus 2 times log log of L divided by L0 plus 1 divided by 1 minus D0. Okay. And let me revert this as minus 2 log of L divided by L0 e to the minus W square, W0 square, because this thing here now, it's going to be 1 divided by W square divided by W0 square. Okay, this. Okay, so I want to bring it into the logarithm, so this becomes W square divided W0 W square, okay, like this. The plus. And there is a factor of 2, yes, here. Okay, so I have this, and then I have minus 2 logarithm of L divided by xi of W. Okay. Now, xi seems to depend not only on W, but also on L0 and W0 square. But because of the RG equation, this dependence is fictitious. If I change my L0, I take L0 equal 5. In my numerics, W0 will change accordingly in such a way that this product will stay constant. It will only depend on W. Okay? Now, if I invert this function somehow, I invert this function and I get that D is a function of L divided by xi of W. And I get xi of W as well. So, okay, there is a factor of 2. Okay? So, without doing anything, just by looking at this thing here, which is the first correction for D equal 2 that we can have to beta, I have for free the form of the localization length. Right?
Use on the way that T is an analytical function of W.
Yes. You at finite system size, T is an analytic function of W. The non-analyticity comes when I go with larger system size, and the non-analyticity is dictated, the precise form of the non-analyticity is dictated by the normalization group. By the way, yesterday you asked me, is this a conformal fixed point? And then I told you no, but it's a scale invariant fixed point. Okay, conformal symmetry is a little bit more. Okay. Usually scale invariant fixed points are also conformal fixed points. However, in the Anderson model, there are some arguments that have been put forward that this is not true. It's not a scaling invariant fixed, it's a scaling invariant fixed point, but not a conformal fixed point. Okay, so yes, I gave you the answer blunt, but it's a little bit more refined than that. Okay. All right, good. Good. So if you have done this exercise, you would have found this very, very nice result, which is known. I mean, it's not my result. This was known from the 80s. And it actually, when you do numerics in the 2D Anderson model, it's tricky. It's tricky. Okay, this needs to be taken into account.
And this correction, let's say this first term, you get it via weak, let's say via the diagrams that we did.
Yes, you can get this correction from the weak localization
so from the diagram.
correction, exactly, or you can just say the first derivative has to be 0. What is the first thing I can put in there? Of course, this doesn't change. If you change the coefficient here, the result doesn't change. The result is not based on the fact there is a true or no. It's due to the fact that you have a 0 first derivative.
But to decide the sign, you need the diagrams.
To decide the sign, you need the diagrams, yes. Okay, good. Now let's keep seeing what happens when you increase the dimensionality.
If the sign were positive, then length would be a correlation length, would be not localization.
No, yeah, so it will be a correlation length, and it means that there is another transition though. Yes. Yeah. So that length will describe, in some sense, the approach to ETH.
Correct. Okay.
Okay. So you would approach ETH in.
Yeah.
Okay, very good. Right, so if you follow DC, from the numerics, it looks like DC goes more or less like 2 over D. When you increase for example, for D equal 3, it's 0.66. It's actually pretty good approximation, 0.66 to the numerics. You look at the critical point where it crosses, where the data, when the points cross around 0.66. You keep doing this, increase D. At a certain point, when you get to infinite dimensions, you end up on a curve like this. Okay? This curve describes the flow. Actually, let me erase everything else. So we have. This curve describes the flow to the ergodic fixed point. In practice,
and so remind how we obtain this 2 over D.
no, you don't have it. It's not an analytic result. It's just numerics. It has to go to 0 when D goes to infinity. Okay, and it goes like 2 over D. Now, in the numerics, when you look at the data, if you look at our papers, the data looks something like this. If you start close to a small disorder, it does like this. Okay. So, sorry, yes, that's like this. If you start close, they attach earlier. Okay. And then if you go to disorders which are larger and larger, if you go to larger and larger disorders, so these are all starting from the same point. For example, you can start from L0 equals 6. And now this is infinite dimension. So this slope is 1. Okay, like random matrix theory. And I'm talking about the regular random graph. So you start L equals 0, L0 equals 6, and disorder, I don't know, like 1, 2, 3, 4, 5, 6, and we know that the transition is 18 point something, 18.1. Okay? So what are you see these crosses here? These crosses are because you look at the data, and again, as I showed you, as a function of the system size, the data eventually goes to 1. But before going to 1, it has a minimum. Okay, so for example, for disorder equal 12, more or less. Okay. You observe this thing. Okay. If you have a minimum, the speed goes to 0. Okay, and that's the point here. But it's not like the other fixed points, because you arrive with infinite derivative. Okay, this thing here should be perpendicular. Sorry, it's. And what happens is that you look at this minimum. So you see, this is why it's the RRG, like main body numerics, it's deceptive because it shows at the beginning, you look at the beginning, it looks like it wants to go to the localized phase. Then at certain point picks up. Okay, and it keeps doing this. If you increase the disorder, it does this at a larger L. And remember that in the RRG, L is the logarithm of the system size. Okay? So it keeps doing this at a larger L and a smaller d. But we know that there is the transition. Okay. So what's going to happen? Where is the transition here? The part of the curve that was flowing towards beta equal minus infinity. Where is the transition? Do you remember that little line that I've erased that was going straight into the critical point? Well, that little line now is one of these curves that just at a certain point touches the origin. And after you have done this, all the other curves, they just do like this. And they get attached here. Okay. So you have all these parabolas, like square roots actually, the square root singularities, that they do like this. Until they don't do it anymore. When they don't do it anymore, you are on the critical curve. When you go farther than the critical curve, then this parabola essentially just attaches here. Now, why does it attach here? Because if you now have d, which is the localized phase, d, like everything must depend like e to the minus l divided by xi. Okay, if I now do d log d by d log d, which is d log d divided by dl, okay, this is not 1 over d. This is not 1 over d log d anymore. This is just minus 1 over xi. Okay, so beta In the localized phase, it's a point. It's a line of fixed point. The localized phase, it's a line of fixed point. With the terminal point, which is the critical point.
I think that compared, cioè, the fixed point in a one parameter scaling should be by definition beta equal to 0. So what does it mean reaching a
But it's not a one parameter scaling.
Okay.
It's not a one parameter scaling. Okay, this part of the curve of the flow is one parameter scaling because this fixed point is one parameter scaling. So in the vicinity of this point, it's one parameter scaling. It's in the vicinity of this point, it's two parameter scaling.
And also, if I don't know that, let's say, the real curve is the blue one, numerically I recognize that I will tend to think are fixed point, but they are fake fixed point because I'm still in the two parameter like
These ones.
Yes.
Yes. In fact, this is the reason that we got fooled in the numeric several times.
To recognize that they are fake because I see they're continuous and they go to merge in a single curve, so to say.
Yeah.
And for
Yeah.
several curves.
So when you do the numerics, you saw in practice that this thing was actually going to asymptote to a certain point.
Okay.
Okay? And this point changed with the disorder. So we hypothesized at a certain point that there was a multifractal phase.
Yeah.
Okay? But in fact, the multifractal phase is not stable. Okay? The curves arrive with infinite derivatives and you just shoot through and then you go to there. Okay?
So if I don't know anything, the way to realize is just do the full numerics and see that they merge in a single curve. And so
Of course, I mean, this is an artist's depiction of what the numerics actually does, because in fact, this part of the curve obviously is inaccessible. You don't see it, but most of the time, even this part of the curve is inaccessible. Okay, so you see things that go like this. Okay, and then they stop. They are at very small d, and then you don't know where you are, right? So in order to find the transition, what do you have to do is to follow the
real transition.
Yes, it's a real transition. It's the Anderson transition on the regular random graph.
Yeah, sorry.
When in order to follow the transition, you need to follow these things, how they go down. Okay, and the way they go down is if you call these points dA, okay? So dA as a function of disorder, they look like this. And then you cannot follow them anymore because your system size is too large, you don't see the minimum. But then if you extrapolate this linearly, you get 18.1. Yes.
How to make a simple argument that this D is e to minus L over psi, L is log B?
A simple argument in the localized phase? It's very easy actually. Just take psi as being e to the minus x divided by psi and compute this sum here. You will get that this is like 1 minus exponentially small correction in the system size. S, the entropy.
How to go from B to L? Because B is the number of sides.
And L is the log of the number of sides. It's the diameter of the regular random graph. So it's maximum distance you have from the localization center when you do this sum. In the paper we have this thing here. In principle, I could reconstruct it. So take a localized wave function here in a finite system with all the exponentially small corrections toward the normalization and so on and so forth. Compute the entropy. The entropy is going to be something of order 1, which does not depend on the system size, plus exponentially small corrections in the system size. Then you take the derivative, the exponentially small corrections count. Okay, so d depends exponentially e to the minus L over xi.
So both of P is L. So you have the derivative over L of E to minus L. Just the same.
If I give you this, you get this. Do you agree? Okay, so this is trivial. The not trivial thing is how do you get this? And my answer is, if you put a localized wave function in the entropy, you compute the entropy with the exponential small corrections, okay? And then you take the derivative, you will see that you get just the exponential small corrections survive, right? But in principle, for example, for phi r, I cannot make the same argument because I don't know how to compute r, but I know that they have to be exponentially small corrections. Okay? Because everything is exponentially small correction. If you compute something else, the participation ratio, for example, P2, again, you will have exponentially small corrections in the system size. Okay? Now, fine. Now it looks like this two-parameter scaling can be described by the function beta, this part here, okay, around beta plus or minus square root of d minus dA. Okay? Let me give you this because there is this square root singularity, right? Fine. The critical point.
But
D is larger than dA because dA is the minimum. D goes like bump and then goes up.
because you showed that you're describing this.
Yeah. Any of these curves, D is always larger than dA.
Right. To the right from D, right? Not.
There is, for any curve, there is no left of dA. dA is the minimum point of the curve. I look at this curve and it goes up to dA and then goes up. I look at this curve, goes up to its dA and then goes up. Yeah, dA depends on the disorder. Okay. Now, let me show you one thing. First of all, if you go on the critical curve, dA is equal to 0, and we have d log d by dl, okay, is equal to beta, which is minus square root of d, okay? So again, this is dd over d to the 3 half is equal to L minus L0, okay, sorry, dl, okay, let's do this. Okay, so when I integrate, I get 1 over square root of d minus 1 over square root of d0 is equal to L minus L0. Okay, and this gives me that d is essentially some constant divided by L squared, L plus another constant squared. Okay, so this means that d as a function of L, the critical point, it goes to 0 like 1 over L squared. Okay, if you look at the numerics, this is exactly what happens. And this is a very important signal that we're actually capturing things correctly. Good. Other thing,
Instead, let's say, in the case of the real Kylie tree, the blue curve will go straight on the axis, right?
for the theory tree, this blue curve does not exist.
Okay. Or simply become the axis.
there is a line of fixed points.
Okay.
The K3, you have this.
Exactly, so let's say, so
You have two lines of fixed points,
correct.
one localized and one multifractal.
And
Okay,
you, so.
and there is a critical
So you
point.
eat, let's say, okay.
And you need in some way.
Okay. And so if I do the numerics there, the hairs will be on that arms that I have there.
Yes, actually, and it's pretty resilient. The Kelly tree doesn't have hairs, just trajectories that go into.
So
You don't have subleading corrections.
So even with the numerics, I'm directly
Yeah, the numerics becomes more complicated when you close the K3, but otherwise it's just an iteration. This some works not you wouldn't see this figure, but the phenomenology is described in some works by Montus and Garel.
Okay.
Or you can leave it open. Leave it open.
Awesome.
Okay, good. So how can we get this equation here? Can we get it from a very simple phenomenology? Okay. So let's discuss in the localized phase. Okay, so remember, what are we doing? We were doing this merging, right? Of our, we are doing this block decimation of the regular random graph. We have that beta is minus 1 over xi. And if we are deep in the localized phase, now I have to do one step of my RG, and I have to take this, everything as becomes a single block. Okay? And I'm asking, how is my localization length changing when I merge these blocks together? If the disorder is huge, there is no change in the localization length, right? There is nothing that can change my localization length because I merged, there are no resonances. But if there are some resonances, I should expect that the localization length, the xi in the log B, now in the, when I change the scaling in the RG, this should be positive, right? If there are resonances. Okay? So, what is a measure of resonances at hand? Oh, I don't know, phi, d. Okay? D measures if there are resonances. If there are no resonances, d is 0. If there are resonances, d starts growing away from 0. So let me write this as d. Let me say, so if d, so d of 1 minus psi, okay, in d log, now I exchange v and b as I did before, right? Because they are interchangeable variables, okay. This is d psi over xi square in d log v, okay. Now this has to be positive, there are resonances. So let me just say it's proportional to d. Okay, if d is equal to 0, I don't have any renormalization of my localization length. If d is positive, I have some renormalization of my localization length. So this is another equation now, d beta by d log v is equal to d. Maybe there are other things like d squares and so forth. I don't care. I'm working really close to the point here. So now I have two equations. One is the definition, which is beta is equal to d log d divided by d log v. And the other is my renormalization of the localization length. D beta by d log v is equal to d. Now I need to use an exercise to prove that you can, that this gives you this. And now I have two parameter scaling. I have two equations. Beta is my second parameter. I'm using beta, which is the localization length minus 1 over the localization length when the disorder is very large, and I'm bootstrapping the significance of beta also when the localization length would be negative. This is the beauty of the renormalization group. You can do this. Take a quantity which has a meaning somewhere and say, okay, this quantity here is something like this, and then it's its own quantity. Okay, so these two equations are equivalent to this. Okay, and they give this 1 over L square. The other thing you can check is that this actually gives you this actually gives you, and then I have to stop, I think. This actually gives you the entire phenomenology. It will give you a critical exponent 1/2 here. Psi is W minus WC, WC minus W, no, sorry, W minus WC. Anyway, let me put set to the minus 1/2 here. And here it will give you a volume associated to dA, okay, which is the critical volume associated with the time that you spend close to this point here.
So it's a measure of how large I should be to see that this is a fake.
Yes, yes. And this VA is the exponential of this 1 over the square root of dA. Okay, just from this equation. Solve this equation now, not with dA equal to 0, with dA finite. You will see that the time it takes for you to get out of this minimum is exponential of 1 over square root of dA. And now the renormalization group cannot tell me what is the dependence of dA on the disorder, but that I can get from the numerics, and I see that dA is linear in the disorder. Okay, so this volume is exponential of 1 divided by square root of WC minus W. And the localization length here, okay, it's W minus WC to the minus 1/2, square root of dA. Okay. It's okay. So the same thing. This 1 over L squared. Obviously, it's phi will behave like this also. So the R parameter behaves like that, like that.
So I'm confused. Wasn't the localization the new in localized as well?
Yes, exactly. So this is a very good point. So this description in which I take something that works in the delocalized phase and I bootstrap to the localized phase, I get this square root. Okay? As I told you before, on the localized side, there should be the localization length goes -1 for the regular random graph, but not for the limit of d that goes to infinity of a d-dimensional lattice. There you get to 1/2. So in the regular random graph, in some sense, once you are in the localized phase, you realize you're not the limit of d that goes to infinity of a regular lattice. Okay. You see that there are no loops. Okay, and the localization length exponent goes to -1. At least this is my interpretation. If you are close to where things become messy and you start seeing the big loops, then the two things are indistinguishable. A d-dimensional lattice with the large D and the regular random graph, they are indistinguishable. Okay. My message to finish is that this is, you see, describing the transition is a much richer picture than just doing data collapse. And this should be a lesson for everybody who wants to do numerics on many-body localization or breaking of ergodicity in many-body systems. Because most likely the transition is of this kind, which, by the way, we were not the first one to see that, to say that the transition is more Kosterlitz-Thouless. There are several papers before us based on other arguments on strong disorder RG and other things that suggest that the transition might actually be described by Kosterlitz-Thouless, and therefore it's not just a matter of just rescaling and putting them together. You need to analyze the topology of the flow. And yeah, and this is a research line which is still open. For example, this thing that Piotr said, the reconciliation of -1 alpha 1 is something which still bothers us. The application of this thing to many-body numerics is something that we have been doing in the past couple of years with some degree of, of success, but not completely, I'm not completely satisfied of the understanding that we have of that numerics. In particular, because if you do the same thing for the XXZ chain with disorder, you see, you follow the minima, for example, of the R parameter, okay? And the minima, they go straight, on the straight line, which would extrapolate at the usual something like 4, okay, disorder for 3.5, 4, okay? But then, the other points you can get, they deviate from this thing. Okay, so clearly there is some strong in some sense, this second equation is, it's stronger. The corrections are strong. There is a strong correction to localization due to the resonances. Okay, and I mean, this thing could be pushed now. If you fit the last 3 points, you get to something like 7 or 8, or you can even say that this actually goes and never touches the axis. Okay, so this line here will correspond to infinite disorder. The RG does not distinguish what are the microscopic values of the parameters that are needed to give you that. They just say there is such a curve. Now go figure out what's the critical, the values of the microscopic parameters that put you in this curve. Okay. So it's a research project. It's many research projects actually, and I think it's important because we need to understand what are the critical theories of these ergodicity breaking transitions. We don't know yet.
As a rule of thumb, suppose that I compute for a certain problem, the R ratios, and I try to do the usual collapse and I don't see any indication of any drifting up. I'm somehow in the situation that I can believe that I can trust the data collapse.
Yes.
Okay.
Or, yeah, I mean, if everything fits, yes. But then it would be like a regular Wilson Fisher fixed.
And when they were in the 3D Anderson, and let's say they didn't see any drift, so at that time was somehow an indication that they were in the right framework.
Yes.
So while doing this RG, is there any assumption on the disorder? Like, is there, will it work for correlated disorder or something else, or I don't know. So there is no assumption.
There is no assumption. Yeah. In fact, we don't write the equations for the RG. We write just the definition in some sense, okay? And then we let the computer tell us what the equations are, okay? So there is no, I mean, one could write a supersymmetric model for the Anderson model, and then, but then, as far as I know, nobody has actually ever done RG on that. There is no small parameter. How do you do that? And then you have to do like Wilson fit, or maybe Migdal-Kadanoff, like block decimation on a supersymmetric theory is kind of complicated. Nobody's ever done that. So there are.
At this level, it is phenomenology. That's what.
At this level, is phenomenology, driven by the data.
Driven by the.
Yes.
Maybe a naive question. So you always use some parameters which are derivatives, like D is the derivative of anticipation entropy.
Yes.
What if I consider different things? For example, logarithm of IPR divided by logarithm of V instead of the derivative.
I don't like take ratios of things because they introduce a lot of they increase the subleading terms. But in principle, you could do it. I mean, you feel, suppose you have, instead of having the derivative of the IPR, okay, instead of having d log p by d log v, you want log v, log p over log v, right? Sure. The first thing I will tell you is that actually, if you know this, you know this. You integrate and you divide by log. Right? So when you integrate, however, you amplify the subleading terms. If this thing has some subleading terms, then you integrate, and if these coefficients are small, for example, I'm just saying something trivial.
This diagram, you can have T larger than 1.
Oh, you can get d larger than 1.
Yeah, take the rate.
Yeah, it's true.
So it means that, right.
It doesn't matter.
You can have D larger than 1, which is kind of physical, but
No, it's not physical because it flows to 1. It flows to 1 from the right instead of from the left. Yeah, it's fine. It's okay. It's subleading. If you go from this to this, you change the weight of the subleading terms, and even the sign of the subleading terms sometimes. Okay, so you can move this to the left. If you're talking about the one parameter scaling part, that shouldn't change. The airs will change.
but the hairs will be one with logarithm of L instead of one over whatever, right? They will be worse in the sense of the ratio, right? Because there is one of the logarithm of velocity.
No, and in principle, I mean, if that goes like, that gives you log P2, d log P2 by d log V. It gives you something like L to the minus Y, okay? When you integrate this, L is log V, okay? When you integrate this, you have 1 over Y, okay? And then you divide. And you remove this, but you're left with this. Okay.
We have a question. So, this type of, not many, but Anderson model.
Yes.
In usual dimension, not in infinite dimension.
Yes.
This quantity, does it give you more information compared to the conductance? Or do you learn more? Or something?
It's just
So if I have the conductance, I still will have the similar picture.
Yes.
Okay.
The problem is that in the numerics, modern numerics is difficult to get a conductor. I mean, you have to do what you want to do. Kuba formula.
Read. Landover.
Oh, scattering. Oh, okay. Okay, yes. Yeah, you could do that. Yes.
Does not require reading.
Yeah, that doesn't require D. It should scale the same thing. If the physics isn't affected.
then the question like this P2 or R-T60 depend on the location of the spectrum. If you look at the mobility age, what should we do? It's not like if it's not homogeneous across the spectrum. There is additional parameter energy
Yes,
in the game, which is hidden here.
it's hidden here.
So, but if you change energy, for example,
Yes.
the mobility age at some finite time here, you will see, oh, depending on energy in the different parts of this.
You are on a different curve. Okay, this curve can be also if you fix W and you change the energy.
Exactly, this curve is
Yeah.
supposed to be a curve that he fixed, like.
Yes, I fixed the, yeah, sorry, I didn't say this at the beginning, you fix it. But it's, there is always it's the parameter that drives the transition could be the energy. You fix the disorder and you change the energy. When you hit the mobility edge, you find exactly the same thing.
Is it possible to do the same if I have non-homogeneous system, even on average?
Non-homogeneous systems,
Like if I do something with Krylov space, like I'm considering D in the Krylov space.
like?
In the Krylov space, like I take any Victorian, I go to the Krylov space, I calculate D there, that basis. It will be like from the very beginning, it's a homogeneous system, right? So it means that even at the same energy, it can be different D.
Right.
So it's not a good parameter to have just energy.
I don't know. I haven't thought about it.
How much this VA associated with the time that you have to get off this?
Yeah, so look at this, right? Take this thing here and let's look at the equation. Then you'll solve the equation, but let me just write down the issue. The issue is the following. So I have d log d divided by d log v is equal to beta. Okay, so let me say we are from below minus square root of d minus dA. Now I have dd divided by d square root of d minus dA is equal to minus d log v. Now you see that the velocity goes to zero, although it goes to zero with the square root. So you don't, the acceleration is not zero. Okay, so you pass through the minimum. But now, where do you pass through the minimum? Essentially, when you're close to the minimum, this d here is essentially dA. Okay, so it takes a long time to, when it takes a long time if dA is small. Okay, now, exercise for you, solve this equation. And the solution of this equation is d of v is, if I remember correctly, is dA divided by cosine squared of v L times square root of dA, something like this. Okay, there's a cosine square because it's periodic, it's just going, and then there is L square root of dA here, there is dA here. Now the question is, if you want to go from, if dA is very small, if you want to go away from dA very small to d order 1, in order for d to be order 1, cosine is to be order dA. Let's say cosine is to be close to 0. So the argument is to be close to pi half, sorry. Cosine becomes 0 at pi half. Okay, and then now you see that you get this thing here.
So the closer that you have to be a equal to 0, this will define the.
Yes. And you see this in the numerics because the more this goes down, the more it slows down, which can fool some people to say that, this is just slowing and slowing and slowing. In particular, if you don't know that there is a transition like in the regular random graph, you might be fooled to think that there is no transition. All right, I will stop here.
Okay, so we can say that the entire program is over. Thanks everybody for being here, and thanks for The discussions, the
We
questions.
should take the main organizer.
No, yes.